second talk, Christian Haase, about reflective politopes. So, thank you.
So the announcement was just made then?
The announcement of.
Mike's?
Oh, yeah, so. And maybe we can like wait until some people come in and then remind people at the end.
I think it'll remind people at the end.
Yeah.
This time I have a little bit more of audience participation prepared. So maybe get your, if you're working on a tablet, get your graph paper background out. So here's the quick answer to the question in the title. If P is a full dimensional a lattice polytope with unique interior lattice points, which I take to be the origin, then the following are equivalent, and in that case, I will call the polytope reflexive. So I write down the criteria, and then we can discuss each criterion if there's notions that you don't fully understand, maybe, or something. Line under this to make this a vector. Ooh. Running out of space just for the definition. Okay. So, yeah, so this so every facet has distance 1 from the origin. You remember the way I measure distances? That means I take the hyperplane generated by this facet, and I take the parallel hyperplane through the origin, and there's no lattice points between the two. Okay, that's what this means. The polar dual of P, so P, so yeah, and also I keep the notation from last time, right? So R is this toric ring, which I get by placing P at height 1 in an additional dimension, take the cone over it, look at all the lattice points in that cone, take the semi-group algebra, that's R. Right, so the P is a polytope in the lattice M, and then P dual or P polar is the set of all points in, well, the vector space associated with the lattice N, the dual lattice, so that y comma x greater than or equal to -1 all x in P. So I kind of so in polytope land you would write less than or equal to 1 because you look at autonomals. In algebraic geometry land or commutative algebra land, people always minimize, so they say this is greater than or equal to -1. Certainly the origin satisfies all these inequalities. And so we know that P is given by linear inequalities. I normalize all the right-hand sides to 1, kind of, and then in that sense, this is the set of all valid inequalities. And we will see a little bit about that. All right. This is a lattice point counting property that if you dilate your polytope by a factor of k and you look at the interior lattice points, you could just dilate it a little bit less. And so this is the Hilbert function of R in degree k. And so this is really just a combinatorial. This is a generating function. This is the Hilbert series. So this is just a direct translation into generating functions of this, right? So you kind of invert all the, you have this rational function in T, okay.
That's the interior lattice points.
Yeah.
Yeah.
Okay, and kind of, this is also should also ring a bell that we have this condition. This is Gorenstein of index 1 because at the very beginning I have required that I have an interior lattice point. Right? Last time I said polytope is Gorenstein if and only if the numerator of the Hilbert function is palindromic. That's what this says. But it's really palindromic of full degree. That's what this T to the D is. So if your Gorenstein of a higher Gorenstein index, this is Gorenstein index 1. If you're Gorenstein of a higher Gorenstein index, this will, you will see that here, and you will see that here.
Freie says at the end of Tuesday's talk, you mentioned this process of shrinking inside the polytope, where you take the interior points in their hull and the interior points in their hull.
I will, if we have time, I will flash some pictures of precisely this process.
So if you do the process with the reflexive polytope, you go all the way in just 1 point.
That's right. Yes. And for the reflexive polytope, your process and my process are actually the same.
See, but it's different for a general.
My process would be to move the facets in at the same speed. That's not the same thing.
The generic hypersurface of any degree.
So again, I'm lying a little bit. So let's assume P is very ample. Then XP sits inside, naturally inside a projector space, a hyperplane. Generic hyperplanes hyperplane sections.
Like a hypersurface, you give, I think, it's their combination of monomials represented as lattice points.
That's right. So the degree is P. Yeah. Yeah, that was badly copied from my notes. Okay. Does anyone want to see a proof of any of these?
So I understand how 6 follows from adjustment form.
Yes.
How does 6 imply one of the others? Is that the same, is it just reversing?
I would think so, yeah. Yeah. Okay. And as I said, by the simple requirement that there's a unique interior lattice point, there's only a finite number of them. Okay. So my first exercise for you is find me a polytope which has a unique interior lattice point, but which is not reflexive. Right. Don't try dimension 2. That would be my hint. Because in dimension 2, this is the same. Or maybe before we discuss this exercise, do we have an example? Do you guys have an example of reflexive polytopes? So, yes.
You could make like diamond containing the or like a circle.
Like the cross polytope. You take the convex hull of plus all the standard unit vectors and minus all the standard unit vectors. What's the dual of that? Yeah, so here examples. So the cross polytope works in every dimension, and the dual of it is the plus minus 1 cube. Okay. And this in dimension 3 might be a good starting point for the exercise. You can talk to your neighbor.
That in dimension 3, you mean like P1 cross P1 cross P1?
With O of 2, 2, 2.
Ah, I see. You need it. Wait, why? Oh yeah, 2, 2. Okay. Confused about something. If you wiggle any of these polytopes a little bit, you'll get more interior points, but they're not lattice points. Sorry, they're not lattice polytopes.
Yeah, wiggling lattice polytopes is you're not gonna get a lattice polytope. Yeah. What?
I think I have an example. I'm not sure.
Maybe let's give the others a little bit.
Thank you. Then I do.
Oh yeah, no.
Let me try to render Okay, and now what I do? So this is kind of, here's the origin, right? This is, all edges have length 2.
Shave off a corner.
And now you cut off a corner here by making the polytope smaller. By making the polytope smaller, you certainly didn't gain any additional interior lattice points, but you gained a facet. And this facet, in fact, has distance 2 from the origin.
The corners first.
Oh, yeah. That's the 3 corners.
Wait, sorry, can you define the distance again? What is the-
Yes, absolutely. I will define the distance. So let's do it in this example.
Yeah.
Okay.
Yeah.
So if I chose my coordinates correctly, then this polytope now that I've here is given by the set of all x, y, z in R3, so that -1 is less than or equal to x, y, z is less than or equal to 1, and x plus y plus z is less than or equal to 2. Okay, so I write down inequalities here, and I write them down in such a way that the coefficients of my linear functional are coprime. Okay, so this is kind of the, so this I should think of as the vector 1, 1, 1 in N paired with the vector x, y, z in M. I like to think of vectors in N as row vectors, vectors in M as column vectors. Then I want this to be a primitive lattice vector. So these should all be integers, and this should not be a multiple of an integer, of another integer vector, other than -1, I guess. Okay, and then the value of this linear functional at the facet and at the origin, they're distant, they're 2 apart. The fact that these are coprime means that like the image is all of z. That's what it means. Okay, so every integer is actually attained by some lattice point. And so if this is like, this is the sum of 2 standard, this is a 1, 1, 0 vector, so the sum is 2. Okay, so the distance, the lattice distance of 2 parallel hyperplanes, I take the primitive normal vector and I just take the difference of the values. That counts how many parallel lattice hyperplanes I have that hit actual lattice points. Okay?
So then the orange one is distance, wait, no,
Two.
okay.
Orange one is distance 2. Is this 2?
Yeah.
Because the standard unit vector is here. It's on this facet in the middle. And this is too far away. This would be distance 1 from the origin.
All of those lattice points lie on these hyperplanes given by x plus y, so that is equal to some integer. For the lattice points on that facet, that integer is 2.
Okay.
For the origin, it's 0. And so their distance is 2 apart. And there's lattice points in between the standard basis vectors that are distance 1. So if you slide that hyperplane along, you hit some other lattice points before you hit 0. That's what it means to have distance more than.
Right, if you look at, so in this case, both of these lattice polytopes would have an R, would have a ring, which is Goranstein. What is the relationship between those two?
This is mirror symmetry. So yeah, I mean, essentially, it's complicated, but there seems to be a relation.
So what are they in these two, in this example of the two duals?
I don't know. This is the second Veronese of the standard of the Segre embedding of P1 times P1. And this one, I don't know. Does it have a name?
But I
Yeah.
guess I was wondering what are the relations maybe, like what does the ideal look like or something like that, but it's okay if you don't know off the top of your head.
Yeah, I mean, I can write down the relations. There are lots of relations, and this would be kind of part of a topic that we didn't talk about. So here the relations are actually very simple. It's this times this is this squared, and this times this is this squared. So the cross polytope, actually, I can write down the relations in general for in any dimension. Here, I mean, you have to write down a lot of relations. You would triangulate this regularly, unimodularly, then you look at all the non-faces, so this and this. I mean, I can guarantee you it's quadratically generated. But here's a non-face, here's a non-face, here's a you write all the minimal non-faces, compute all the trailing terms. Those are the relations. There's a lot of relations here already.
I think it's more geometric is the relationship. It's algebraic. This is the way you get these mirror pair Claudiads.
Yeah, so what you can do, which would yet be another topic involving the counting of lattice points, is you can compute the Hodge diamonds of these hypersurfaces from the lattice point counting stuff. And their mirror symmetry is actually proved.
So there's no relation, there's no clear relationship between the ideals or the Betty numbers of the syzygies or anything.
So,
okay.
Certainly if you use the adjective clear, there's no such thing. I mean, there's a very deep relationship between certain combinations of lattice point counts of different faces of the two polytopes. So there's one way to combine these on one side, one way to combine these on the other side, and then you realize that the Hodge diamonds really are, well, mirror dual to each other. Right. So I wanted to give you a few numbers to get a feeling. So in dimension 1, I have one reflexive polytope of one polytope with a unique interior lattice point, and it is in fact smooth. In dimension 2, I have 16 reflexive polytopes. I have 16 polytopes with a unique interior lattice point, and I have 5 of them are smooth. In dimension 3, I have 4,319 reflexive polytopes. I have 674,688 with a unique interior lattice point, one of which we found. Smooth reflexive, I have 18. In dimension 4, the number of reflexive lattice polytopes is half a billion. Who knows? And 124. Those were actually classified by Victor Batarev in his PhD thesis. Well, 123 of them were found, and then somebody else found the last missing one. And then, like everything else, is of course, this is completely out of the question. So this goes on a little bit, 866, 7622, 72256. Smooth reflexive polytopes in the respective dimension.
And to be clear, reflexive requires a single interior lattice point.
Yes.
Okay. Yeah, right.
So this number has to be bigger than that.
That all the time. Okay. It doesn't say reflexive.
Oh, yeah. Write that down instead of.
Oh, yeah. The definition is missing. If any of these equivalent conditions are satisfied, then it's called reflexive. I didn't write that. I didn't write that down. And right. So I gave you these numbers just to show you something to yes.
These all to like lattice isomorphism?
Absolutely. Yeah. So of course, I mean, you know, there's also this reflexive polygon, which I would not consider different from that. Because otherwise, I mean, you can pull this arbitrarily far, so there would be infinitely many. So this is up to isomorphism. Yeah, I just want to share an open problem with you. How do these sequences grow? This one I know grows at least doubly exponentially. This one clearly grows only exponentially, right? You get 1 digit more per line. So this is factor of 10 maybe from line to line. Can you prove that this is bounded by 1,000,000 to the d? That would be something. Then very few would. I mean, it's clear that very few are smooth of these guys. But then we would have also an asymptotic dichotomy here.
How do you see smoothness? Can I see smoothness in any of these realms? Like, for instance, if it's a polytope was smooth, would R be further nice somehow, or I don't know.
Well, it's the product of it is smooth, right? I mean, this.
The product is smooth. Can I read the? So you're saying the only singular locus is the origin?
Yeah. So it's this condition on like this is smooth because at every vertex I see a lattice basis. This is not smooth.
Oh, right. So the polar of a smooth is not necessarily smooth. So
it will certainly almost never be smooth. Smooth, you need simple, and then the dual is simplicial. And simple and simplicial, then you're either a simplex or a polygon. Okay, I was gonna do one more exercise, but I'm gonna skip it. So let me cut to my theorems. Theorem 1. So from the finiteness, you would think that being reflexive is very, very restrictive. And I mean, it is. There's only finitely many in every dimension. But if you allow the ambient dimension to grow arbitrarily, then you have a very complicated lattice polytope in your hand. You will find another reflexive polytope in high dimensions where this one occurs, or is I mean, it's isomorphic to a face of that reflexive polytope. Nope. So there's you can, I mean, if you have, once you have this theorem, you can so there's no restriction. I mean, there cannot be a restriction because there's infinitely many lattice polytopes already in dimension 1. And then if you would restrict the dimension, then you would only get a finite number of things. So but what you can do is you can define the reflexive dimension of a lattice polytope to be the smallest dimension of a reflexive polytope so that this occurs. And so I have a few results on like how does this behave with respect to dilation? What's the reflexive dimension of a segment? And there's upper and lower bound, but it's not monotone. Like a segment of length 11 will occur in a 4-dimensional reflexive polytope, but not in a 3-dimensional reflexive polytope. Whereas a segment of length 12 does occur in a 3-dimensional polytope. So there's a doubly exponential, like the simplices I've presented last time. There's one edge which has doubly exponential length. But in terms of lower bound, I can only prove square root of the logarithm. So log of the length is kind of one end, and square root of log is the other. Excuse me? Yes, yes. D equals 2 P reflexive.
The volume was if you take the Hilbert series and you plug in 1, correct?
The numerator of the Hilbert series, yes.
The numerator, yeah.
Yeah, which is, so in this times it's just 2 times the Euclidean volume. It's just d factorial times the standard volume.
Figure out if this could be written in terms of the Hilbert series or its numerator either. Like,
Oh yeah. I mean in this case like the Hilbert series is palindromic, right? So the Hilbert series, so Hilb of P, that's 1 minus t cubed, and it has 1 plus something times t plus t squared. And so this is here b minus 2. B is the volume.
so the point is that if you take and then what is the sorry. So this is Hilbert P, and P polar would have the same, well, not the
No.
same, but with a different coefficient, no?
Yes, I mean you
Okay.
plug in 12 minus v.
Exactly, okay. So the sum of them, okay, would be like just 2 and then
2, 12, 2. Yeah, that would be the sum of the two. There's a different way to express this theorem. And where's my?
So then in dimension 2, you can read off the dual pulse from the Hilbert.
Absolutely, absolutely. Yeah. I mean, there the hypersurface are elliptic curves. There you can, yes, in dimension, like this is in dimension 2, everything works. In dimension 3, nothing works, essentially.
So like a
And that's-
generalization of this theorem to dimension 3 would be like nonsense, or just people don't know it yet?
So there's a beautiful theorem, which I want to write down. D equals 3, P reflexive. Then if I take E an edge of P, right, then the polar dual has a corresponding face, which in dimension 3 is again an edge. Okay, so I can take the length of E, I can take the length of the polar edge, I can multiply them, I can sum it up, I get 24. No, it's not the polar of an edge. It's so here we have the, let's say we have the cube, and then the polar of it is now I have to draw
Oh, I see, you mean
an octahedron.
the thing that corresponds to an edge in the polar.
Yes.
Okay, understood.
So then you have this polarity exchange. So every vertex here corresponds to a facet, and every edge here corresponds to an edge here.
Right.
And this is the thing. So in this example, these edges all have length 2. These edges all have length 1. So I'm multiplying 2 times 1. And there's 12 edges. Okay, so let me prove this for you. Well, these things, there's 16 of them, they're classified. Done.
You can write down the 16 and show that it's true.
So for the rest of the time, I could give you an idea of this proof, or I could give you an idea of this proof. Or I can, because the runner-up in the vote was minimal model program and adjunction, I could flash some pictures of the adjunction process. What do people want? I mean, the online people have no pictures. Okay, let's do pictures. I have to hold this down. Oh wait, let me try. I hope this setup works. So you can see pictures there already.
That there are 16 numbers across.
Okay, so this is kind of still of this first half of the talk. Another exercise, if you get bored, try to pair them up. This is really a good exercise because you need to apply isomorphisms at some point, and then this helps you getting a grips of this isomorphism of lattice polytopes. Yeah, so here. Okay, so this one and this one are dual to each other. We have already established that. Okay. So I've butchered slides from a talk I gave about this stuff, and can I move this somewhere down? No. No, it goes away. Yeah, that's my last name means hair in German. So that's been my symbol since I was a teenager. And okay, so here are the pictures. Okay, so here's a polytope, and in a junction theory in the minimal model program, we take a polarized variety. There's a polarized variety for you, and you start adding the canonical divisor to your divisor and see what happens. So for a toric variety, the canonical divisor has a coefficient -1 on each ray of the fan, which means, move all the facets inwards, all at the same speed, and just see what happens. Nothing happens, nothing happens, nothing happens. Woof. Okay, so at some point, the polytope will shrink to something lower dimensional, which then can either be a point, like in the reflexive case, right? You do this we already had this observation. In the reflexive case, if you do this, you will end up with a single point, and that tells you something. Or you end up with something of positive dimension. Then you have, in a certain sense, a vibration. You can project away this space and get some information from there. Okay, here's another picture. Because again, in dimension 2, you don't see what really happens. So we start moving things inward. Nothing happens. At some point, this top edge contracts. And the combinatorics of the polytope changes, even though it's still full dimensional. If you continue, a new edge appears. Okay, it goes in the other direction. In terms of the minimal model program, what we've done is a flip. We've left the Neff cone. We started at D. We walk along in direction of K. We hit a wall. And in junction theory, this value where this happens, where the first time the combinatorics changes, is the Neff value. And so this can happen. New edges can appear. And let me also mention here, if you do this in dimension 2 all the time, you think the only thing that can happen is that facets disappear. No, the facets are all there. All facets that were there, like all normal vectors that were facets previously, still are. But still, I mean, facets can disappear. And at some point, you have a dimension drop, and that point where this happens has several names. It's the pseudo-effective threshold, the negative Kodaira energy.
Where you hit the boundary of pseudo-effective.
That's right. The combinatorics have changed before. Here. So I mean, this you can really, in the polytope land, you can really formalize this very nicely. Like you have the pseudo-effective cone is a polyhedral cone. It has a polyhedral subdivision. into chambers, which correspond to these different combinatorial types you can have with a given set of rays. Yeah, and you can then go ahead and prove some theorems about it. So here's my more formal definition. Okay, so yeah, so I have a polytope P sitting in R to the D, and then I look at all the facet defining inequalities. And I move them in by the same amount S. That's the process you've seen.
That's the question. I'm realizing I'm pretty naive way earlier, that if you play this game with a Gorenstein Fano polytope, you just get a multiple of it. You just get the multiple. It's because it is the anti-canonical.
Yeah.
It is.
Yeah, exactly.
You're just adding self.
Exactly.
Staying in the same color.
Yeah, so this really is the inverse of the pseudo-effective threshold, but in polytope land, this is much more natural to consider this. It's the supremum of all the amounts that I can shift this in and still get a point out, at least. Okay. From this, if you then translate existing adjunction theoretic theorems into polytope land, you can get actually quite some mileage out. You can classify smooth three-dimensional polytopes without interior lattice points. This is just a direct translation of Fujita's classification result using adjunction theory. I found that pretty nice. But I also wanted to mention that really what we've done so far is the wrong thing. This is far too complicated. So what we should do is not look at facet defining inequalities. You should look at all valid inequalities and move all valid inequalities in. So in algebraic geometry, in the minimal model program, you want to stay kind of in the same Picard group all the time, because then you know what the canonical is, and then it stays across walls, it stays the canonical, and you know what to do. In this polyhedral land, we can actually talk about all valid inequalities in terms of, I want my coefficient vector to be a non-zero integer vector. The polytope is every point in the polytope. If you replace the bullet by any point in the polytope, it's a true statement.
Think so. Hyperplane's not corresponding to facets.
That's right. That's the idea. So this goes back. This is called the fine polyhedral adjunction theory, because Jonathan Fine, in his thesis, considered kind of P upper F of 1.
Make this geometric, something like all toric varieties for a fixed torus.
Yeah, I mean, you want to do birational geometry with toric varieties is kind of silly, right? Because they're all birational. Yeah, but I think you want to look at all resolutions or something and look at the exceptional divisors. Yeah. So in this example, the two processes already differ at a very small step because this vertex here is very singular. And what you get at the epsilon is in fact what people call the canonical resolution of singularities in the minimal model program. Yeah, so these processes then can differ significantly. So this one stops earlier, right? This is and it stops in a different dimension. Of course, you define the same thing, and then the core, the last thing that remains, in this case it's a segment, in this case it's a point. They don't have anything to do with each other really, right? So here one contains the other, here the other contains the one, but they can also be disjoint. This goes okay. So this is just an example to show that this is a less than or equal sign here. This is kind of the old stuff. If you project it down, you project away the core, this eta value does not go up. But if you do the fine version of it, it just stays the same. Okay, so here's the core for the standard adjunction is this segment you see there, and the core for the fine adjunction is this two-dimensional thing. So kind of the reason for me to point this out in this group is my algebraic geometry is too weak, but there should be, like, inspired by this stuff, there should be some sort of minimal model program or so in algebraic geometry, which I mean the results are stronger and the proofs are easier. So it's really a much better behaved theory. Yes.
Like, so I took something corresponding to an ideal, like optimum module section ideal in my brain. The original is like taking symbolic powers. But then what this is, like, you know, this is like
Original symbolic power.
like taking what do you call it? Like taking these like higher and higher things where you're just taking considering facet. Yeah, it's just like before you what do you call it? Sorry. But before you take the fine version.
The adjoint polytope?
Yeah, just the I don't know
Like the smaller one.
Keep this up. Like actually start with like a canonical module that's actually an ideal. Then P to the n is like so the monomials in it.
No.
It's not-
No, they're getting fewer and fewer, right?
So yeah, higher next symbolic power is great.
Actually, well, here's a question.
Well, I guess okay, so I guess I'm thinking of like taking an affine clone over it and then you know what I'm like
Yeah, so I think like this is like instead of just translating into a normal projective variety, or you do the original core, you're shrinking the inequalities on divisorial valuations that only come from the toric variety, from the fan you started with.
Yes.
Here you're allowing to take the Reese algebras or ideals or any of these constructions you would get by intersecting the primary ideals that you get from divisorial valuations, where it can be literally any valuation on the Laurent polynomial ring that comes from the dual lattice, right? So these have a geometric it's like, there's a few adjectives, it's like divisorial valuation, maybe it's like integral divisorial valuation. But like cluster algebraists think about these a lot. Like the set of all of them, rather than just the ones that you get that appear on your given compactification of your interior, which is of course. And so, yeah, I think it might not be going the right way, but it's like, yeah, you intersect you look at all divisorial valuations and you look at the original powers that gave you your your section space lives in.
Yeah.
And now what happens if you take every single one of those valuations and you shrink that threshold by one, right? Every single one of them.
Yeah.
You're still getting a space of rational functions. It's still a vector space of rational functions. It still satisfies these inequalities, but it will change a lot more than if you obviously. So I think this is the story of that. I don't know if that has a name in commutative algebra or algebraic geometry, but these kind of things show up in at least Fano geometry and cluster algebra, like compactifications of log Calabi-Yau. You consider things like this.
Okay.
Like the key being, instead of only looking at a finite number of valuations and looking at kind of all the natural valuations that satisfy these criteria. And when you do this for a torus, you get exactly the lattice points in the dual in the co-character lattice.
Yeah.
I'm sure this could be, I could see this being well behaved, right? But I think these are primary ideals that you get, right? When you take a ring, you take a valuation, and you look at all of the things in the ring that are bigger than or equal to R with respect to that valuation. I think this is always a primary idea. And symbolic powers come about naturally from this, because you take a right, but I mean, symbolic powers will come up when you take, I'm sorry, when you take a divisor. So something like codimension one.
Yeah, I guess these are negative small numbers. He's going in. It could also go out, I guess, if you were going out, that's what I'm saying, but yeah.
Yeah, going out in this other sense that's not fun.
I see.
So with if you restrict to your facets, going out makes sense, but like going out when you look at all, you can take a really long vector, and going out with respect to a really long vector by one is just hardly moving at all. So if you really intersect all, you're getting the polytope back.
I think it's still intersecting things that are ideals when you're viewing them with the right ring. But it's like a section space, right? With the section space, you take everything bigger than here, everything bigger than here, everything bigger than here, right? And if you looked at each of those individually, there would be a DVR and an ideal in that DVR. But when you intersect them all in the rational functions, you get a finite dimension. Right? This is section spaces on normal varieties, right? Are all like this. They're all some little vector space inside of the rational functions that satisfy some inequalities. So the question is, how rich of your algebra or alphabet of inequalities are you admitting? Right?
Yeah.
All with places on the variety, or just the ones that come from divisors that are present on.
All right, I think my time is up. Thanks for.
Indeed. Any questions on Zoom from mostly Brett, I guess? Cool. Thanks for joining, everyone.